All right, so here's an example of putting the analysis of variance test into motion. In this example, this is an experiment where mice are randomly assigned to four different groups, and each group is exposed to a different level of a substance. In this case, it's red dye, and so the categorical variable here is simply which group the mouse is in. So group 1, 2, 3, or 4 is a category. And then the quantitative variable that we're testing is just the lifespan of the mouse, so how long the mice lives in weeks. And so again, we're trying to see if there's an association between the amount of red dye exposure, in other words, which group they're in, and how long the mouse lives. The groups are broken up into dosage levels. So the first group is the control group, meaning they have no exposure to anything in particular. The second group, group 2, is the group that gets a low dosage of the red dye. Group 3 gets a medium dosage, and group 4 gets a high dosage. So this is all the data. You can see my groups are not the same size, and so that'll have an impact on my assumptions. They're not terribly different from each other, but that will have an effect on our assumptions that we'll talk about later. And so here's how we can set up the analysis of variance test. We're going to use a significance level of 10% here. That's not that unusual in the life sciences, especially when you're working with living things that where you have a reason why your sample size might be small. So the significance level of 10%. So the first thing we have to do is carefully state the population means that we are studying. Mu1 will be the mean time of death for mice with no exposure. So notice that the mice that that are in my sample are basically randomly chosen from this group, from the group of all mice with no exposure. It's very important here to remember that these are population proportions. So these are the mean time of death for the mice who would have these different exposures to red dye, not just the ones that I did the experiment on. So our null hypothesis is that the means are all the same. So mu1, mu2, mu3, mu4 are all the same. So if that were true, that would mean that which group you were in, the level of exposure, has absolutely nothing to do with how long you live. In other words, there's no association at all between which group you're in and how long you live. So the null hypothesis is always the statement that there's no association between the variables. HA, the technical statement would be that this is not true, that at least one of these is different. That would be the technical way of saying it. But intuitively, what we think of HA is that there is some association. There is something going on where being in one of these groups makes your mean time of death different from the others. I will say analysis of variance, don't forget that all we're doing here is seeing if there is any difference at all between the means. It doesn't tell us whether they're all different. It doesn't tell us whether one's higher or lower. It just tells us that something is different among these four different population means. So if I put this information into a piece of technology, so I'm using here the web app that with the link that's shown on the screen, and all I have to do to use this tool is tell it how many groups I'm using. It'll give me boxes for each group, and then I'm just copying and pasting the data from each column of my table into the boxes that are there, and that's all the information I have to specify. One of the nice things about analysis of variance, unlike some of our previous significance tests, is that the null hypothesis and alternative hypothesis are always the same. The null hypothesis is always that there's no association between category and response variable, and the alternative hypothesis is that there is some association. And so because of that, when we're using a piece of technology, we don't have to actually enter anything in about what our hypotheses are, because the hypotheses are always the same. So when we do that, we get a graph. It shows us our four groups as side-by-side box plots. It does tell us over on the right side the means, and they're denoted with little triangles on there. So we have little triangles here. And so these means being different from each other is what the what we're testing for. And it looks like probably if there is one that's different, it's probably that one. These don't look terribly different, but this one's quite different. One thing to be a little concerned about from the assumptions point of view is how spread out group 4 is compared to these other ones. Like these seem to have about the same variability. That's a little more, and this is a lot more. So that might weigh in on our assumptions in terms of having a valid conclusion. The output of this app is very minimal, and I'll talk about these numbers in the context of the StatCrunch output because it gives us more information. But it's all here as well. The things to point out at this point is that this is the F test statistic, and this was the thing we were talking about being the between group variability divided by the within group variability. That's what the F was. And so that's being measured at 3.62. That number in and of itself doesn't mean a whole lot to us because there are lots and lots of F distributions depending on the sample sizes. So the number by itself is not going to be terribly meaningful. But we use the F statistic to get the p-value. And the p-value is the probability, just like it was before, it's the probability of getting data as far away from normal. Well, is the probability of getting data like you did based on the null hypothesis being true. So, so a small value there means that that there's a certain level of incompatibility between the null hypothesis and the data. And we've learned that when there's that incompatibility between the null hypothesis and the data, that we should doubt the null hypothesis. We should reject the null hypothesis. So in particular, notice that this p-value is less than 0.1. That was my significance level. So therefore, I would reject H0. So before we go to writing our conclusions, let me just show you what the output looks like if I put this into StatCrunch instead. And you can use either one of the things. It doesn't matter, but I want you to see both. The ANOVA test for StatCrunch has a very similar input where you just tell it you're going to do 4 groups. For the one I chose, I put the 4 groups of data into 4 different columns because I just copy and pasted from the table over to the StatCrunch. Notice that that StatCrunch actually gives us a little more information. In particular, rather than draw the picture, it tells us the summary statistics for our data, and this is where we can kind of see that we're out of line with our assumptions. This is the biggest standard deviation. That's the smallest, and if we read the details in the textbook or one of the slides I wrote earlier, it said that that when our sample sizes are not the same, we really would like to kind of contain things so that the standard deviations are not too different from each other. And the rule of thumb was that we wanted the biggest standard deviation to be no more than twice the smallest standard deviation. And you can see we've violated that by quite a lot here. So probably with this sample size and these standard deviations, we really would not be able to make much of a case that our conclusions were super valid. But that's not really the point of this example. Really, we were just trying to make sure we understand where all these numbers come from. All right, so let me take just a second to explain where the numbers come from. And I never will calculate these by hand, but I do want you to have some sense for these things. SS means sum of squares, and MS means mean squares. So the M there, the M here is the word mean or average. The numbers over here are degrees of freedom, just like we've seen before. But notice there are 2 different degrees of freedom, and that's why we really have no chance of doing this with any kind of tables. This degrees of freedom is always 1 less than the number of groups. So this is the between groups information. Since there were 4 groups, there are the degrees of freedom is 3, 1 less than that. This is a little weirder. This 34, it's technically the total sample size minus the number of groups, but really what it is you take the for each group, take 1 less than the sample size and then add up those different degrees of freedom. So it's really the sum of the degrees of freedom for each of the four groups added together. Again, those don't matter in terms of calculating them yourself, but I wanted just to point out that those are based on the number of groups and the amount of data that you have. So the way these numbers are calculated, the thing called MS is just the number called SS, sum of squares, divided by the degrees of freedom. So for example, in the thing that says columns, that's our between groups variation. The SS number is 412.9, and the degrees of freedom is 3. And if you do that quotient, you'll get the 1371 or whatever that MS number is. And then the same thing for here. So if I divide 12,876 by 34, I'll get this guy. Dividing 412 times by 3 gives us this guy. The F that you see there is really the MS for between groups. In other words, the first MS number divided by the second MS number. And so the 1370 over 378 is about 3.6 apparently. So that's where that number comes from. So then the only other thing is, what about this p-value? And again, we're not going to actually compute this in any way, but the distribution of possible F statistics looks like this. It looks like a skewed right distribution, goes through 0, 0. It does not go to the left of the axis at all. So this is the distribution of F scores that you could have. And there's a slightly different picture for every possible combination of degrees of freedom here. So there's tons and tons of these F pictures. They all look like that, but they're slightly different depending on the degrees of freedom. So the important thing here is that the particular F score would be a line that we're drawing, and that's the same thing that happened in the other, I'll write the number down, 3.62. That's the same thing that happened with our other significance test. The test statistic, either the z-score or the t-score, was a vertical line on our picture, and then the p-value is how much is shaded in the tail. So this is what the picture looks like for how p-value and F scores are related to each other. Like I said, it'll always look more or less like this. We don't have a way of generating these pictures ourselves, but the computer can draw them for us. What else was I going to say about this? Oh yeah, notice that that it makes sense that the higher the F score, as long as the degrees of freedom aren't changeable. So for the same picture, the F score being higher means the p-value is lower. So the higher the F, the more you move this guy to the right, the amount of area that you have will be less. So the higher the F score, the lower the p-value. But if you remember, our intuition was that a higher F score meant that we had more evidence of an association. And so we have the final conclusion that the lower the p-value, the more evidence we have in association. But that's actually just the conclusion we would have had anyway. We did paid attention to our H0. Oh, see, it does a better picture of it. Our H0 and our J. So here's how our conclusion would work without having to think carefully about all of those different numbers. In our case, we got a p-value of about 2%. And remember, our significance level was 10%. So 0.02 is definitely less than 0.10. Since that's small, we reject the null hypothesis, and then we say we have significant evidence to claim or to conclude And then we, as best we can, write HA, right? So our statement here, just like it was before, if we reject H0, rejecting H0 means supporting HA. And our HA, if we go back and look at it, was the statement that different dosages of red dye are associated with different average lifespans for mice. Or more specifically, was just that one of those population means mu was different than the others. And the way we could say it in the language we talked about earlier in the course is here. This is another way of saying HA. There is an association between the exposure of red dye and the lifespan of a mouse. That is a very nice, very non-technical way of stating the HA that allows us to have the ANOVA test always end up with a conclusion about association between the variables.